Well, good morning. Good morning, everyone. My name is Ignacio Raez, and I work at NanoGap. NanoGap is the responsible for the dissemination and exploitation of the Back to Fuel project. Okay, we have organized a series of webinars that will try to explain the different disciplines we tackle within Back to Fuel project. Yesterday we addressed the conversation towards atomic quantum clusters. And today we are gonna talk about photocatalytic processes. We are gonna do the same as yesterday. I'm gonna introduce a little bit about Back to Fuel, and then I will leave the floor to Andung. Andung, he is a research assistant at the Technical University Berlin. And the University of Berlin is the responsible for the photocatalytic process, and he will talk. He will give us a lecture about the work they are doing. Okay, and I will start by sharing just an introduction of what Back to Fuel is about. Okay, it's an acronym of bacterial conversion of CO2 and renewable hydrogen into biofuels. Okay, the idea is to demonstrate at TRL5, technology readiness level 5, the possibility to produce biofuels, ethanol, butanol, and hexanol from water, sunlight, and CO2 by coupling different technologies. There are two main methodologies within Back to Fuel. The first one is a photocatalytic process where we use the sunlight and we use a catalyst that has been added, the atomic quantum clusters we saw yesterday, and we are able to split the water and produce hydrogen. This hydrogen will feed a bacteria in a second step. This bacteria will feed with CO2, and we are analyzing two possible techniques. One of them is bioelectrochemical system, and the other one is a fermentation process where we produce the biofuels, the acids, and then the biofuels. What we do is to modify as well the bacteria by CRISPR-Cas in order to enhance and improve the selectivity to produce something concrete. I mean, if we want to produce butanol or if we want to produce ethanol, we modify by genetic editing, we modify their genes in order to produce exactly this and optimize the energy towards the production of these biofuels. So we couple nanotechnology, biotechnology, nanotechnology in the use of clusters at sub-nanometer particles to produce hydrogen, biotechnology in the use of CRISPR-Cas and in the use of bioelectrochemical systems, chemical engineering, because we need to couple both technologies and be able to demonstrate it at TRL5, and also economy, because the idea of the project is to get commercialization faster than expected. We are at TRL5, and our idea is to reach TRL9 in less than 7 years. That's the expected idea. So that's the reason why we have 6 webinars. Yesterday we took nanotechnology. Today we are gonna see the photocatalytic process. That means coupling nanotechnology and chemical engineering. Then chemical engineering, how to couple biotechnology. Tomorrow we are gonna see CRISPR-Cas, and on Thursday we will see bioelectrochemical systems. And at the end, on Friday, we will see an overview of the whole project, and then the economy. What are the steps that we need to address in order to reach commercialization? Okay. The consortium is based on 4 universities, and 2 companies. NanoGap, USC, and Lancaster are more related to clusters, how to characterize synthesis, production, and optimization. Then Vito is the responsible for the bioelectrochemical systems. Wageningen University is the responsible for CRISPR-Cas, the modification of the bacteria. And Berlin is the responsible for the photo production part, and then the coupling, is the responsible to couple the both technologies, okay, and scaling up the whole process together with the rest of the consortium for sure. Okay, so as we have seen now, the whole project as it is today, we are gonna see the photo production part. And Andung, I give you the floor. The floor is yours, and well, go ahead and good luck.
Okay, hello everyone. My name is Anh Dung, and I'm working in the group of Professor Schomaker in Berlin. And today I want to talk about how to test a photocatalytic system. And as introduction, I only gonna show you a video. And in this video, it's a video a colleague of mine recorded several years ago. And here you can see a photocatalytic reactor setup. And the photocatalytic system here contains carbon nitride. And as you can see here, we also used a sacrificial agent, and with incident light, it produces hydrogen. But as you can see here, there was a first thing you should avoid if you do experiments with photocatalysts. So here you can see the hydrogen bubbles evolving. And now the main question is, how could we measure such experiments, or how could we measure such photocatalytic systems? And how is it even possible to compare it with other groups? Because if you're in the field of photocatalysis, you will see that it's very hard to compare results between groups, because the conditions, the reaction conditions are different with each group. So for the first, I'm just showing you our screening reactor. It's a very simple double jack glass reactor with an input and an output for a thermostat to control the cooling temperature. And we have a reaction chamber where the photocatalytic process where it reacts with the light. So this is a picture of the very simple setup in action. So you see, you don't need anything, just the reactor, a magnetic stirrer, and a lamp. And we have pro and contras for this kind of setup. So a pro argument is that we have a very large irradiation area and a very small headspace in this kind of reactor. So even the smallest amount of hydrogen or what gas you want to detect can be detected with this kind of photoreactor. It is very easy to handle the experiments with this kind of reactor, and it's very cheap. Some negative arguments about this kind of reactor are that the result is most of the time an estimation of the evolved gas, the amount of evolved gas, as you always just take a gas sample out of the reactor at the top and analyze it with a gas chromatograph as example. We also have an unknown operating temperature. I can show it to you in the next slides. Why we don't know the temperature in this kind of reactor. And the most difficult, the most difficult thing about this kind of reactor is you won't get a time resolved volume of the evolved gas. So you don't have a time plot from the volume to the time. So because all of these negative sides from this reactor, our group just designed a standardized photoreactor setup for our laboratory to do measurements in the liquid phase. And this kind of this kind of reactor you saw just here is very popular among most of the groups. So we just designed a standardized photoreactor setup. Here you can see like a small schematic drawing. We have here our photoreactor, a thermocouple inside of the liquid to measure the temperature. Here you have a lamp, a dosing valve to be sure what kind of gases evolved. After each reaction, you can open the dosing valve and take a gas sample out of the headspace to analyze it in the gas chromatograph. Then you have an extra gas tank here. If the amount of hydrogen or gas, whatever you want, evolved is too large, then you can open this extra gas tank to run the reaction even longer. Then you have a manometer and a pressure sensor. The pressure sensor is very important just to detect the amount of evolved gas during the reaction. A thermostat here is for the cooling of the whole system to have a constant operating temperature, and the magnetic stirrer is to have a homogeneous suspension. This is how our photoreactor looks like. So you have here the pressure sensor, which is connected to a computer. You have the manometer, but the pressure sensor does the same job as the manometer. Here you only get a look if you calibrate the pressure sensor. The extra tank safety valve if the pressure inside the reactor is getting too big. The dosing valve to get your sample after the reaction. And here is the connection to the thermostat, the reaction chamber, the thermocouple inside of the reaction chamber, and a magnetic stirrer to steer the whole solution with the particles inside. So this is how a reaction would look like. And this is the defined reaction chamber with a irradiation area of 12.25 square centimeters. This is important, and in the following slides, I will explain to you why. So what do we get out of this kind of experiments? You will get a time plot from the pressure. And here you can see the cooling temperature of the thermostat. This is the temperature inside of the reactor, and this is the set temperature. In this kind of experiments, we couldn't go below this cooling temperature because then our cooling fluid would, or the water would be frozen, and you couldn't cool the system anymore. So this was the temperature we got after the 40 minutes for our reaction. And after the reaction, you get like a CSV data from the pressure and the time and the temperatures. And from this, you can get a gradient. And with the ideal gas law, you can calculate the amount of, or the amount of, here was it hydrogen over amount of time. So in this example, it's 0.0133 liter per hour. And the main question now is, how can you compare this number to the numbers or the results of other groups? Because if you are reading publications from most of the other groups, you will see something like we could produce 200 micromoles of hydrogen with each hour or with each hour per gram. But the reaction conditions at each experiment's varying. So for this, it's very important that we have a known irradiation area. In our case, it's 12.25 square centimeters. You also need to have, you also have to know the light intensity of the light of the irradiation source you have. We used a 300-watt xenon lamp, and with a 395 nanometer cutoff filter, which absorbs photons with energy higher than 3.14 electron volt. Yeah, and with this known light intensity and with this known irradiation area, you can calculate the quantum efficiency. And this kind of numbers are comparable to the numbers of other groups, because the volume evolved per hour or per time isn't accurate enough, because it depends on the light source, it depends on the reactor you are using, it depends on the irradiation area, and there are too many conditions you have to care about. So to standardize it, there are two efficiencies, the solar to hydrogen efficiency and the quantum efficiency. Solar to hydrogen efficiency most of the times is used when you are using a solar simulator with power of 1000 watt per square meters. And as we used a xenon lamp in the last experiment, we just calculated the quantum efficiency with the amount of absorbed photons. So we knew the band gap of this photocatalyst. It was titanium dioxide with platinum on the surface as co-catalyst to improve the hydrogen evolution reaction. And with this kind of numbers, we got 0.145% of quantum efficiency, which is quite low. But it's just to demonstrate you how to measure this kind of photocatalyst in a standardized condition. So to get a correct solar to hydrogen efficiency and quantum efficiency, it's also very important that all the incident light will get absorbed. So I think you already heard something about the Lambert-Burr law. And here you can see that it's dependent on the concentration, and after a certain amount of concentration, the amount of absorbed photons will stay the same, or of the light. So there's an optimum concentration where you won't get a higher solar to hydrogen efficiency, even if you put more of your photocatalyst inside of your photocatalytic system. So for our experiments to get the quantum efficiency, we just took the data from the lamp manufacturer and plotted it in origin and calculated the fractions of each wavelength, just to get to know how many photons of a certain wavelength got absorbed. So the second thing I want to talk about is our gas phase photoreactor setup. The last photoreactor setup was for measuring photocatalyst in a liquid phase. Now in our project, we want to collect or to concentrate the sunlight with parabolic mirrors or solar concentrators in general. So you will also concentrate the infrared parts of the light, and it will also increase your operating temperature. So we will work with water vapor or gaseous water. And for this, we have a photoreactor setup for the gas phase. So this is a small flow sheet of our setup. So here you have the different MFCs to control or to fill our reactor with different kind of gases. For our experiments, we just need argon and water. And with this controlled evaporator unit, you can get water vapor inside of the reactor. The pipes are heated to a certain temperatures to prevent the condensation of water inside of the pipes. And then in the reactor, you will heat the whole system up to 200 or 300 degrees. And after the reaction here, you have your light incoming. And after the reaction, you can, or we can measuring the results with a mass spectrometer, as you can see here. So this is how this setup looks like. Here are the MFCs. Here is the controlled evaporator. It will go down here. Here you have the photoreactor. Here you would have the light, which would here you would have the light, and here is the connection to the mass spectrometer. This is how the reactor looks like from above. And this is the kind of result you will get out of this kind of experiments. It's very important that you notice the pressure of the reactor at the beginning of your measurement. So you can do the material balance with the mass spectrometer results. As a reference gas, we are using argon, which is inert and won't react. So we can compare everything with argon from the beginning with the volume we have at the beginning of our experiment. So with this equations, we would get the hydrogen evolution rate for our photocatalytic system in a gaseous phase. In the gas phase, and with the known irradiation area, it's 13 square centimeters, and we also can calculate the amount we can also calculate the solar to hydrogen efficiency and the quantum efficiency. So as a conclusion or as a take-home message is that the results between groups are very hard to compare if some conditions are not given. So you should think about the following conditions before you test your photocatalytic system, just to be sure that you can compare your results with a colleague, because the amount of hydrogen evolved in one setup will change drastically, even with the smallest changes in your photocatalytic setup. So what you have to take in mind is you have a defined irradiation area, you have a known lamp intensity, and this have to be checked regularly before experiments, because all of the lamps are losing their power or their intensity over the time. So be sure that you check the light intensity between your experiments. Then you also have to always have a defined distance between the lamp and your photoreactor. And this should be measured too. We always measure it with a photodiode. And from there, we know the power of our light at a certain distance. Then what is very important is that you have correct evaluation methods, because when I read some publication, it's always hard for me to understand how can they calculate this amount of hydrogen if they don't know, as example, in the batch process, if they don't know the pressure inside of the reactor. So it's always a rough estimation in most of the times. Then you should be sure that all the light should be absorbed from the photocatalytic system. It means that the concentration of the photocatalyst inside of your liquid phase should be high enough. At a certain point, the solar to hydrogen efficiency and the quantum efficiency won't change anymore. So you have like an optimal concentration inside of your liquid, but the activity per mass unit will change drastically. So it's very important for the upscaling that you have optimum concentration inside of your system. And for the quantum efficiency, we just did it with this kind of integration of our lamp spectra, but the most accurate results would be if you use a monochromatic filter to only have light or with a given wavelength. So do you have any questions about how to test photocatalytic systems, or questions in general, how to evaluate results?
Thank you, Andung. Yeah, I think there are some questions. You can send the questions through the chat during the presentation or after. So I think it was, thank you. It was really, really interesting. I think the video, I don't know if we can see again the video
Of course.
because it quite nice to see how the hydrogen is.
At the video, you can also see what I mean with this is a video which they recorded for a previous project with the name Light to Hydrogen.
Mm-hmm.
And if you take a look at this setup,
Mm-hmm.
you can see that it's very hard to, like here you can see it's very hard to define the irradiation area.
Mm-hmm. Yeah.
As you can see here, it's a circle. You can't say, okay, what kind of this reactor part is absorbing the light. So because of this, we designed this new, or all our new designs are made with a flat surface. So we can say exactly how the irradiation area is without the estimation.
And you were saying that there is already a size, no, of the
Yeah,
reactor.
irradiation. Yeah.
So why this size of the reactor? Is a template or is something calculated beforehand and then examined? I mean, if it is 12 square centimeters or whatever, why, or can we modify the size or not? It's just
Yeah,
it's fixed.
you can modify the size of the of your reactor as you wish. The only thing you have to take in mind is that you have this part, or this given irradiation area, because it's very important to calculate the amount of incident photons with a given light intensity to calculate correctly your solar to hydrogen efficiency or your quantum efficiency, because only this kind of data is comparable to other photocatalytic systems.
Okay.
So if you give some volumes or some activity per gram or per hour per gram, it's very hard to compare because the reaction conditions are different between each group. The one group is using a solar simulator, the other group is using a xenon lamp, 300 watt xenon lamp. The other group is using a 200 watt xenon lamp with a 395 nanometer cutoff filter. So it's very important to know this kind of data to compare the results between each other.
And what about the catalyst of this project you mentioned? How do they do it?
At the moment, you mean the photocatalytic system we are developing inside of our project with the atomic quantum clusters?
Because I see on the chat that there is a question about the use of titanium dioxide and platinum, and
Okay.
so why are necessary both, or if it is why the use of both instead of use just one, or is this a standard use?
Why we use both? This is just a very popular
Mhm.
photocatalytic system. You have titanium dioxide as one of the most well-known or most researched photocatalysts at the
Mhm.
moment. And you have platinum, which is very good for the hydrogen evolution reaction as a co-catalyst. It can separate the charges. And with this photocatalytic system, we only wanted to show how our system is working. And at the moment where we did this kind of experiments, um, we also investigated what different deposition methods or how different deposition methods will increase our activity and will increase the quantum efficiency.
Well, so people, if you have any questions, it's the moment to ask. Now, if not, I have several questions here. Well, why is it so hard to compare the results from other groups?
The thing is, other groups have other kind of reactor setups or
Mm-hmm.
photocatalytic setups, photoreactor setups. And if you read some publications, you will see that they just gonna mention, okay, we used a 300 watt nanometer, 300 watt xenon lamp, or we used a solar simulator, but they don't give a accurate data of their reactor design. So you only know, okay, you have this kind of lamp, but you don't know the distance, because with the distance, the amount of incident photons will decrease. So if it's farther away, you won't have the same intensity as if it's very near to the reactor. The second thing is you don't have the irradiation area in most of this kind of results. So it's very hard to compare this volume or this activity of the photocatalytic system, because it could be that they have a very high activity because they have like a very large irradiation area and a very strong lamp.
So that there is no pattern to follow.
Yeah,
No,
yeah,
for every application, for every group, or they are.
yeah. Until now, there is no pattern. So most of the good publications always mention this quantum efficiency or the solar to hydrogen efficiency.
Mm-hmm.
And this kind of efficiency you only can get if you have an irradiation area, a known irradiation area, and light intensity. And most important is that the concentration of the photocatalyst inside your system is high enough, so you don't have um, extinction anymore,
Mm-hmm.
or you have the highest extinction. So that every light or every photon which gets into this photocatalytic system is getting
Developed.
absorbed.
Uh-huh. So, but that's not easy at all, no?
No, there are.
Well, there is another question from Angel.
Okay.
Do, do you see the
Yeah,
question
yeah,
right?
I see it. Given that hydrogen.
Mm-hmm. I will say it. Given that hydrogen production is difficult to standardize, is there a way for the industry to know which is the most cost-effective photocatalyst to be applied in their technologies?
Yes, yes. The most effective photocatalyst could be for to compare this kind of catalyst. You can take the solar to hydrogen efficiency. So you have like the amount or the energy evolved, or the energy from the hydrogen you have, divided with the incoming light. And if you have this kind of efficiency, you can compare the photocatalysts performance between each other. And then you can say, okay, this one is very effective, this one is not that effective. And then you have to take a look on the costs of this photocatalyst and about their stability. So maybe one system is very have a very good solar to hydrogen efficiency, but the production costs are too high because they have very a large amount of noble metals like platinum on the surface or ruthenium. So you have to compare it. One, the solar to hydrogen efficiency, and the other way is that you take a look on the costs to produce this kind of photocatalyst.
Okay. Mm-hmm.
You're
Well,
welcome.
well, thank you, Angel. Well, anyone from the chat, if you have any question, please send us. In the meantime, well, I had it here, some others, but what do you think, in your opinion, Andu?
Yeah.
What is the main limitation the main variable, in your opinion, that will move forward or move back on the photocatalyst catalytic reaction? I mean, is the phase, is the gas or liquid phase, is the catalyst, is the clusters, are the clusters, which one
At the one we have
could you
to
choose?
at the one, in my opinion, we have to investigate very um, we have to investigate how the clusters are working together with several semiconductors like titanium dioxide or other support materials. And the main thing we are faced at the moment, or in photocatalysis in general, is the overall water splitting. So if we would do the water splitting with a sacrificial agent, as example with some organic solvents, then we would have a very high hydrogen evolution rate, but the cost, or we want to get biofuels at the end out of it, and the cost would be too much to get hydrogen from this kind of sacrificial agents. So the main bottleneck at the moment is the overall water splitting. It's very hard to do overall water splitting with this kind of systems. So the main approaches at the moment are so-called Z schemes, that you have an electron mediator, hydrogen evolution reaction photocatalyst, and an oxygen evolution reaction photocatalyst. And what we are trying at the moment is that we overall split water in one system, at one nanoparticle, with our atomic quantum clusters. And the main bottleneck we have now is the purification of the atomic quantum clusters, as you know, I think you know already, and the loading. But I think this is a thing we have to investigate more.
Okay. Well, we will accomplish, and we will find out how to purify it and synthesize in just one process. Okay, so I don't know if there are no more questions. We can conclude the webinar. Thank you, Andun, for your extraordinary presentation. I hope the people enjoy today's meeting. I just say a kind reminder for tomorrow. Tomorrow there is another interesting webinar about CRISPR-Cas at 2 p.m. Paris time, Central European time, and you can find the link through the website of Back to Fuel, or you can send me by email an email to me or to Back to Fuel. Any question regarding the webinars, the following webinars, or any other question, and I can forward to Andung, to the University of Berlin, or whatever information you may need. Okay. Thank you so much, and thank you, Andun, again. Thank you all. Have a nice day, and see you tomorrow.
Thank you too for everything, Ignacio, and yeah, see
Bye bye.
you.
See you.
Bye-bye.